Today I'm going to go over phases of matter and phase changes. Make sure my screen. So we did this in class, and I'm just going to go over it in case you missed anything. So solids have a fixed volume and a fixed shape. So do you see the diagram here? Normally we draw all of these, but we can't draw on your computer as easily. So the particles are super close together, and then their intermolecular forces are really strong. So that means the forces that are between two different molecules are really strong because they're very close together. And the solids are moving, so all molecules vibrate. And then some molecules, depending on what state they're in, are able to move. Well, solids don't have a lot of energy, so they're just sitting there vibrating, okay, at their fixed location. In all of the solids that you can look at right in front of you, your pen, your desk, your computer. But liquids have a little bit more energy. So not only are they vibrating, but they can start moving past each other. So my water bottle, the water in there can move a little bit, okay? But my particles in my pen aren't moving. So they can start moving past each other because their intermolecular forces in a liquid aren't as strong. And that's what gives them a fixed volume, but their shape can change. And then lastly, gas has the most energy. So that makes them move all over the place. They're vibrating and they're moving all over the place. So they have no fixed shape or no fixed volume. Their intermolecular forces are very weak because they're not even close to each other. They're very, very far apart. All right. So in our Venn diagram, those would be the things that are unique to just solid, liquids, and gases. But something that's similar between solids and liquids, they have a fixed volume. Something that is similar between liquids and gases, they don't have a fixed shape. And then this one's trickier, solids and gases. It's harder to find just one thing that they have in common, but you could put they have intermolecular forces, they move, even though that is the same that would be the same that you would put in the middle here, that they all have those things, okay? Another reminder, solids are our lowest energy phase, liquids are have a little bit more energy, and gases have the highest amount of energy, and that's going to dictate their behavior. That's also going to help us think about our phase changes. So melting, going from a solid to a liquid, if I have my solid state, which is a lower energy state than a liquid, I need to add heat to be able to melt that solid. Okay, I need to melt that solid. Really, it's breaking apart and breaking apart the intermolecular forces and giving the particles more energy to move around into the liquid phase. But freezing, going from a liquid to a solid, I'm removing heat to fix them into that shape. Okay. And then here's the thing. For evaporation, going from a liquid to a gas, you've probably heard that for a very long time, but really evaporation is just at the surface of the liquid. Vaporization is my entire sample going from a liquid to a gas. And I need to add heat in that instance, okay, to give them more energy to get moving around to be a gas, all right? And then condensation, going from a gas to a liquid, the opposite. I'm going to remove the heat to slow the particles down and get back into the liquid phase. And then the last set, sublimation and deposition. So sublimation is going from a solid directly to a gas. I need to add a lot of energy to go from not moving to moving all around. And then deposition, going from moving all around to a fixed shape. I'm going to remove heat. And then two more definitions on that. Exothermic, giving off heat or releasing heat, and endothermic, taking in that heat. And let me show you our diagram. All right, so here are our graphs. This one is an exothermic graph because do you see how energy has been given off in this circle? to the circle, into the system, and we are left with more energy over here, okay? So if it's out of the circle, it's exothermic. If it's into the circle, it's endothermic. All right, that's how we would graphically represent our energy for a phase change or chemical. These ones are just phase, but we could also we'll revisit these graphs when we talk about chemical reactions, okay? So if you have any questions, let me know. Good luck.